discoveries of physicists since 1930 has given us a remarkable insight into the fundamental structure of matter in our universe. So all the matter in our universe are made up of fundamental particles which could be broadly classified as leptons and quarks. So in our previous lecture, we had a small glimpse into what leptons are, and in today's lecture, we'll be seeing more about quarks and be taking one step deeper into elementary particle physics. So let's start with a small recap about our previous lecture, where we classified subatomic particles into leptons and hadrons based on their response to strong interaction. Now leptons, they are elementary particles, which means that they cannot be divided into subsequent smaller particles. And we had examples for leptons as electrons, muons, tau particles. Then we had their neutrinos, electron neutrino, muon neutrino, tau neutrino. So these 6 particles formed leptons, and we had its corresponding antiparticles too. The second classification was hadrons, and hadrons are composite particles, which means that they can be further divided into constituent particles. And these hadrons are composed of elementary particles called quarks, which forms the topic of our today's lecture. So let's see more about quarks. As I have already mentioned, quarks are elementary particles. They are the fundamental constituents of matter. So just like leptons, we have quarks also, which are elementary particles, and they cannot be divided into further constituent particles. Right. Now these quarks have some peculiar properties. They cannot be observed individually. It is impossible to isolate a single quark. So this is totally unheard of, because we can isolate an electron, we can isolate a neutrino. They are all elementary particles. But when we come to quarks, it is practically impossible to isolate a single quark. Why? We will see that in upcoming slides. Another peculiar property of quarks is they possess fractional charge. Now we are familiar with charge, and the smallest charge that we know is the electronic charge. And we express all other charges in the universe in terms of this electronic charge. But quarks, they possess fractional charge, which means that a quark can have a charge of, say, 1/3 electron charge, or maybe 2/3 electron charge. So quark can possess fractional charges, and also they have their own antiparticles, and we call them obviously antiquarks. Now these quarks, we have already seen, they combine together, or they composes the hadrons. Now hadrons, we have further classified them into mesons and baryons. Mesons are bosons, which means they are energy carrying particles, and baryons, they are fermions, which means they constitute matter. Now all the mesons, they are made up of a quark and an antiquark pair, whereas all baryons are made up of 3 different quarks. Also, in the case of baryons, we will be having antiparticles also. Just like when you say a proton is a baryon, it will be composed of 3 quarks. And if you have an antiproton, we represent it like this, it will be composed of 3 antiquarks. So this is what a quark model suggests. Let's see different type of quarks. So quarks, they were identified in 3 different generations. The first generation quarks, they are up quark and down quark. The second generation quarks are strange and charm quarks. And the third generation quarks are top and bottom quarks. So the first generation quarks, they are more stable and they are less massive. And as we go to higher generations, the quarks become more unstable and they become more massive, and they decay into the quarks of like the lower generation, the first generation quarks. So we are having totally 6 different quarks, and we call them as flavors. So the different quark flavors we have are up, down, straight, top and bottom. Now these are some of the properties of the quark flavors. As we have already seen, the quarks, they have fractional charges. So the up quark, charm quark and top quark, sometimes called as truth quark also, they have a charge of plus 2/3 electronic charge, whereas down quark, strange quark and bottom quark have a charge of minus 1/3 electronic charge. Now they all possess a spin half, a baryon number 1/3, and they have a strangeness number also. Again, we are familiar with strangeness number. Only the strange quark possesses a strangeness number of -1. Now there are further other properties. For charm quarks, it has a charm number which is +1. Now the top quark, it has a top number which is +1. The bottom quark has a bottom number which is -1. But that is totally out of scope for this current lecture. So let's just focus on these given properties of quarks. Using this, let us see how our matter is made up. So, as we know, all the matter that we see are composed of atoms, and atoms are constituted of proton, neutron and electrons. Electrons are by themselves elementary particles, and the proton and neutrons, they are baryons, and as we have already seen, baryons are made up of a combination of 3 quarks. So let's find out which all quarks combine together to form a proton and a neutron. So for a proton, we have the charge +1. The spin of a proton is half. It's a baryon, so baryon number is 1 and strangeness number is 0. So let's find which all quarks corresponds to a proton. As the strangeness number S is equal to 0, we won't be having a strange quark. What is remaining? We need a charge is equal to +1 and a baryon number that is also +1. So in order to get a +1 charge, we'll be having a U quark which is having a charge +2/3. Another U quark. So you have 2/3 charge plus 2/3, that is 4/3. And a D which is -1/3. The total charge will be +1. And each of this quark is having a baryon number 1/3 each. So the baryon number B also will be equal to +1. So we can say that a proton is comprised of 2 U quarks and 1 D quark. So this will be having a spin up, a spin down, again a spin up. So the total spin will be equal to 1/2. Spin will be 1/2. Similarly, when you consider neutron, it is having a charge 0. The strangeness also is 0, which totally omits the probability of having a strange quark. And it's having a baryon number which is equal to 1. So we have 3 quarks. Let's say if you're having a U quark, you'll be having a charge 2/3e. But the total charge is 0, so you'll be having a D quark with a -1/3e and another D quark -1/3e, which gives you a total charge 0. So a UDD quarks represent a neutron. Fine. So this constitutes all of the matter that we see in the universe. So protons and neutrons, they are made up of UUD quarks and UDD quarks respectively. So some similar examples we'll see with mesons and hyperons too. So these are 3 mesons. Again, we are familiar with them. Mesons, we have already said, they are composed of a pair of a quark and an antiquark. So this is a pi plus meson. A pi plus meson is having an electrical charge +1. Baryon number, it is not a baryon, so it is 0. Fine. So let's see what constitutes a pi plus meson. So if you have a U, you'll be having a charge 2/3e. Great. If you have a D, you will be having -1/3e. Fine. But your charge is +1. So this need to be plus, which means that this is an antiquark. So this will give you a total charge of 1 electron. So pi plus, it is made up of U d1, a quark and an antiquark pair. Next is K minus. It's a kaon. The charge of the kaon is -1. Now we are familiar with the class that kaons belong. They were called as the strange particles. Once again, when you rewind, we know that strange particles are those particles which are formed during a strong interaction but decay through a weak interaction. So they have a strangeness quantum number S, which is equal to -1. So what composes a K minus particle? So let's say if you're having U, again it is 2 by 3e. You need a strangeness S equal to -1, so you will be having a strange quark, which is -1 by 3e. And in order to get a total charge of -1, this has to be negative, which means our up quark is an antiquark. So K minus, it is composed of an antiquark of U and a strange quark S. Similarly, we can write K0 bar. This is also a strange particle with strangeness quantum number -1 and total charge is equal to 0. So you can write it as D bar S. D bar will be having a charge 1 by 3e and S is a charge -1 by 3e. So this will be given by D bar S. So this is how you find the quark model of mesons. So now let us see few more examples where we'll deal with hyperons. So hyperons, they are also charged particles. And we are having 4 different hyperons: lambda 0, sigma plus, psi minus and omega minus. So let's see the quark composition of these 4 hyperons. So lambda 0, we are having charge 0 and a strangeness quantum number equal to -1. So this implies that we'll definitely be having one strange quark, which is having a charge -1 by 3e. Now we need a total charge equal to 0, which means that we'll be having 1u and 1d, so that the charges will sum to 0 and strangeness is equal to -1. So a lambda 0 is made up of a u, a d and an s quark. Next we have a sigma plus. Sigma plus is having a charge +1 and a strangeness quantum number -1. Again, it is obvious we'll be having one strange quark and to get a charge +1. So this is having a charge 1 by 3e. You need a plus charge, so you'll be having a 2 by 3e corresponding to that of an up quark. Another up quark, totally the charge will be +1. So a sigma plus is made up of a U-U-S quark. Psi minus is having a charge -1 and strangeness quantum number -2. So this implies we'll be having 2 strange quarks, each of charge 1 by 3e. Now to get a -1 charge, we'll be having a D, which is also carrying a -1e charge. So the total charge is equal to -1 and the strangeness quantum number will be equal to -2. So a psi minus is made up of DSS quarks. And finally we have omega minus. So charge is equal to -1 and strangeness is equal to -3. Again, it is totally obvious that we'll be having 3 strange quarks, each of having charge -1 by 3. So we'll be having a total charge of -1 and a strangeness quantum number of -3. So this is how we find out how each of our hyperons are composed of quarks. Now, it is evident that omega minus, it is composed of 3 s quarks. Now, quarks, as you have seen in their properties, they have a spin half. And all the spin half particles are categorized as fermions. Now, those fermions, they obey an age-old rule called as Pauli's exclusion principle, which means that no two fermion can exist simultaneously in the same quantum state. Now, when we see this, the Pauli's exclusion principle is being violated here. We are having 3 strange quarks. So, how is this possible? We are not supposed to violate Pauli's exclusion principle, and in order to conserve that, we introduced for quarks a new property called as color of the quark. So, quark colors is what satisfies Pauli's exclusion principle for the quarks. So, when we say about color, it is actually like a charge. And we have 3 different colors for quark. They are red, blue and green. Now, when we say red, blue and green, these colors have nothing to do with the physical colors. These are actually color charges. Just like we say charges in the case of an electromagnetic force. In the case of electromagnetic forces, we have 2 different charges, a plus charge and a minus charge. And when we consider the quarks, which interacts with each other through strong force, there we have 3 different charges, and those charges are represented as red, blue and green. So these are color charges, and these colors have nothing to do with the physical colors that we observe. Now, for each of these colored quark, they have their antiparticles that are the anti-colors. So for red, we have an anti-red. For blue, we have anti-blue. And for green, we have anti-green. So these quarks as anti-quarks, with their color property, they combine to form all our hadrons. So when a meson is formed, a colored quark combines with an anti-colored quark. When a baryon is formed, 3 colored quarks will combine. But whatever the case is, once a stable subatomic particle is formed, that particle will be absolutely colorless. Which means that any particle that could be isolated, that could be detected independently, will have as a color property null. So none of the particles that we observe will have this color property. Whereas quarks, they have this property called color, and this property ensures that the quarks cannot be isolated. So we can say that all the colored particles, they are confined. It is impossible to isolate, to independently detect a colored particle. And this property is known as quark confinement. So quarks are colored particles, and hence they are practically impossible to be isolated. So when you have a matter particle, say a proton or a neutron, it will be composed of 3 different quarks, and the color of the quarks will be in such a way that the color of this proton or the neutron, it will be null. The proton or neutron, it will be absolutely colorless. So these quarks are held together by the strongest force in the universe, that is the strong force. So the strong force holds all the quarks together inside our neutron or proton or any matter particle. Now this is a strong force, and strong force is an exchange force, which means that the quarks will interact with each other by exchanging some particles. And these exchange particles are called as gluons. So gluons are the carriers of force in the case of a strong force. So it is practically impossible to separate a quark, but if we supply enough energy, a large amount of energy, so that finally we are able to separate a single quark, separate an isolated quark from this, we'll end up in creating a new quark-anti-quark pair. So once again, it is totally impossible to isolate a single quark. You have to supply a lot of energy, but when we supply a lot of energy, we end up in converting that energy into new matter by creating a new quark-anti-quark pair. So let us see a very small example of that. Here we have one subatomic particle with the quark composition U, D and D, which means that this is a neutron. So we are having three colored quarks here. So the neutron is totally colorless. Now we are supplying a large amount of energy in order to extract a particular quark. We are planning to isolate this blue D quark by supplying a lot of energy. Now all this energy we are supplying, what happens to it is, it will follow the energy equation and this energy will be converted into matter in the form of a quark-antiquark pair. Fine. And then this will split into a UUD, which is a proton, and a quark-antiquark pair. This is a pi minus meso. So when we try to isolate a single quark by supplying a large amount of energy, what happens is this energy is getting converted to matter by following Einstein's energy mass equation. So this matter appears in the form of a quark-antiquark pair, right? Now from this, so you will have UDD and a new pair of quarks, a U and a U bar, which will result in a one proton and one meson. So this happens when we try to separate a quark. We end up in creating a new quark-antiquark pairs. So this is one peculiarity of the strong force, the color force, which maybe we can see in some other lecture. So that's all for today. Thank you.